G. Let's see. Right, so G is the buzzword for G is called is the generator. You can't pick any random G and expect this to work. Okay, so G has to be picked carefully, and we do not have the time to go into the mathematics of where the G comes from. Okay, so you don't have to worry about this for the moment. Any questions on CRC? So the reason, again, we're covering this topic very, very quickly. You can spend an hour or two at least discussing how CRC works. The reason we use CRC over basic internet checksum, it has better error detection properties. Okay. And in particular, you can prove that if you have RCRC bits, of course, you can get as many CRC bits as you want. You can select G accordingly and get more and more CRC bits, and it gives you better error detection. And you're less likely to miss an error. In particular, if you have R bits in a CRC, all bust errors, where you consecutively flip a whole bunch of bits, or a whole bunch of bits suddenly become 0 or 1, all bust errors that are R plus 1 bits or less are guaranteed to be detected by CRC. Okay. The other question here is, this looks like this is a pretty difficult calculation, right? Even for the computer. If you have to write a program to do this, it's going to take a while for that program to run. Okay? Because all these things will take quite a few instructions, and if you have to do it with every data byte that comes, you have to do this whole multiplication, whole process. That is going to be expensive. So how do you get away with it? Why doesn't it just completely block your computer? You're doing so many calculations for every byte or bytes of data that you send. It probably takes much longer to do this calculation than to send the data if you wrote a program to do it. Why is that not the bottleneck? And why do you care if it's a 10 megabit link or 100 megabit link? Because this will probably take more time to calculate than whatever the wire can carry. Any comments? So the short answer there is that all of this is in hardware. Okay. So this is all in your adapter hardware. So your CPU does not participate in this. So, since the adapter has very limited functionality, you can customize the hardware to do exactly these kind of computations. And this is also at least part of the reason why you do not do it at higher layers. You wanted to do this at TCP, that's the next question. Why not everybody do it if this is a smarter way of doing business? But if TCP or UDP was doing it, then your processor has to do all these calculations, and that's going to be really slow it down, while the basic sum is very simple. Okay. So, yes? Software modems, yeah. Yeah. I mean, if you implement a modem in software, you'll have to do these processing. I mean, you have to run the entire link layer protocol. So you would have to do that processing, and you won't run as fast as a hardware modem. Why you want to build a hardware modem? If you want to be able to do all of this processing for $10 at line speed, you can't take a computer and be able to do it. It'll be slower and more expensive if you write a general purpose program. But if all you want to do is test and see things function. Don't worry about speed. You can do it in software. Like that's true of anything. Routing also, you can you can have well, I mean, routing is always in software, but you can have dedicated routers whose hardware is designed for routing, or you can take an ordinary Linux machine and convert it to a router. So it's kind of a similar thing here. Yeah.
CPU may be coming to play based on how fast the CPU is. You have a software model. You have fast CPU, the cost. You probably not slow down too much.
Right. Yeah. So yeah.
That is coming to play.
Right. So CPU speed will matter for a software modem. Here, it doesn't. With the hardware, obviously, it's not that important. Any other questions? Another thing to remember about error detection and correction is that none of these protocols are perfect. There will always be some sequence of errors. If a very precise sequence of ones and zeros are bits, the error detection and correction bits will match. So it's always possible that you have a bunch of errors and they're not detected. What you do with better and better error correction and error detection, mostly error detection, is that you make the probability of errors not being caught very, very small, but it never completely goes away. Okay, so we will cover one more topic today, which will take a little bit of time, and that is multiple access protocols. Okay, what's the idea? There are two types of links in the world or at the link layer. One is point-to-point links. You have your modem. The other end of modem goes to a wire. The wire, connects it to maybe to a modem or the part of the modem at the phone company or something. So you have your computer. A wire goes from there and connects you straight to the router or something. So that's a point-to-point link. You don't have to worry about sharing. You own the whole link. So you don't care about other people. Okay. However, many important links are shared or broadcast links. Okay. So the old-fashioned Ethernet, you had to have a single wire that you connected to from all your machines. So anything that was sent from one computer also went by all the other computers, which means that if the other computers send something at the same time, they'll both collide and nobody will hear anything. You have wireless networks. If multiple people are broadcasting on the same frequency, same time, data gets corrupted and lost. Similarly, for satellite network, it's a shared medium. So the idea here is that how do you manage these so that everybody is not talking at the same time and everything is getting corrupted and nothing gets through? So it's kind of like you have a cocktail party and everybody wants to talk, but if everybody tries to talk at the same time, nobody hears anything. So what is the protocol people follow so that you can have communication going? So that's the basic idea, and a very important topic in link layer and networking in general is these protocols to manage communication when there's a single medium everybody has to use, and those are the multiple access protocols, also called the MAC protocols. So the basic idea again is single shared broadcast channel that everybody has to share. When two or more nodes transmit simultaneously, there is interference. Okay, so interference leads to collision. If a node receives two or more signals at the same time, there's a collision and nobody hears anything. All the data is corrupted. Okay. So to deal with this, you have these MAC protocols. It's a distributed algorithm that everybody in the community that wants to share has to follow so that data goes through. One of the things we assume is that communication about channel sharing must use the channel itself, no out-of-bound channel for coordination. So if a bunch of people are talking, then you could have a designated person, in theory, say, well, now it's your turn, now it's your turn, now it's your turn, and so on. But that is not realistic in the real